And why is he famous? Well, famously, he refused the Fields medal. He refused the clay. You know, the Poincaré conjecture was viewed as, was designated one of the millennial problems. If you can solve this problem, the Clay Foundation is going to give you $1 million, which to mathematicians at least is a lot of money. And he refused that as well. And he's a guy who, and he could have had any job anywhere in the world after he did this, but he didn't want to take it. And he's a bit of a, you know, his hair is funny and he lives with his mother in St. Petersburg or something. I've actually never met him. There was a short period after and he never actually finished proving this stuff. He wrote these, you know, what mathematicians tend to do now is when they have a preprint, something that they think is going to be a paper, they'll put it on the so-called archive, the electronic archive. It's a wonderful way to keep in communication. He put his rough versions of these papers on the archive in 2002. Mathematicians quickly realized that these are very, very important and very likely to be useful, but it took a number of years for mathematicians to actually show that it does really work. Meanwhile, Perelman went back into wherever he came from and stopped interacting with anybody. So this, you know, math is fun, math is wonderful stuff, but I think the public is mainly interested in math when it involves human eccentricities such as, you know, the beautiful mind and Nash and other things. I mean, the age-old problem has to do with relating geometry and topology. Topology is, think of I'll give a simple example again of surfaces. The topology is, for two-dimensional surfaces, is essentially, for closed things, essentially how many holes does it have. So there's the topology of a sphere, which has no holes, topology of a donut, which has one, topology of a double donut has two. That's all about that's the topology of a surface. The curvature is something very different. The curvature is all about how pointy things are in a certain place, these geodesic paths, what the geodesic paths are in getting from one point to another. So the Poincaré conjecture, which was put up by Poincaré in, I forget, around the turn of the last century, around 1900, was a particular a conjecture as a guess, and he claimed that there were these certain relationships between geometry and topology. And then later, Thurston, an important American mathematician of the last 20, 30 years, maybe a little bit longer, he jazzed this up in a much more complicated, inclusive way into a beautiful conjecture, which included the Poincaré conjecture as a special case. People were very, you know, these very old conjectures, people, you know, that can make your fame, make your name in math if you prove one of these things. But people were trying to prove it in certain ways which were very different from the Ricci flow approach. From the point of view of differential equations, they were looking at Riemannian geometries. They were looking at what you would call elliptic partial differential equations, and they were doing many more topological geometric things. This completely different way of saying, okay, we're not going to study the geometry by just having it sit there. We're going to change it. And the thing that change allows you to do is you can start with something fairly complicated, and if you understand the way this change is happening, and if you can show that the change always goes to something you understand, then you've proven something important. In fact, a result of Hamilton's that got this program some interest from the very start that made people pay attention to it. He said if you take a manifold, and we don't know what the topology is, but it has a character of a certain curvature is positive, so-called Ricci curvature is positive. Who knows what that thing looks like? What we'd like to know is we'd like to learn more about it. One way to do it is say, I'm going to change that geometry in accordance with Ricci flow. I understand how the Ricci flow acts, and I'm going to prove that the curvature always goes to exactly that of a sphere. So that was Hamilton's first wonderful result, that no matter what geometry you have, no matter what topology you have, if the curvature, the Ricci curvature, something called Ricci curvature, is positive, it's always going to become a sphere. That tells you that the manifold you had to have has to be a sphere, because only has to be the topology of a sphere, because only the topology of a sphere, up to certain identifications I won't discuss, only the topology of a sphere admits a sphere metric, or let's just say a very restricted class of manifolds admit such a metric. So the key idea of Ricci flow, I'll try to say it again, is rather than study the topology and the geometry in stasis, just fixed there, we're going to say, let's change the geometry in a nice, fairly well understood way, see if we can find an endpoint, and if we can, then we've learned an awful lot.
Is it like trying to understand a famous painting by turning it into a TV show?
You're taking a static problem and you're moving it, and the question so how to relate that metaphor to this is, what do you learn from the TV show? So if you could say you're starting with a static painting, you want to understand the interplay of the colors, and you have some way of changing the painting in such a way that the blues tend to congregate here and the greens tend to congregate there and the colors all do something, and then at the end you have, I mean, one thing you could do, here's a nice, perhaps an analogy. Say you have a very complicated painting, like maybe an Aboriginal painting, and you want to understand for some silly reason how much of it involves the color red, how much of it involves the color blue, etc. If you had some way of deforming, changing the painting so that the blues all go one place, the reds all go another place, the yellows all go another place, then when you're done you see, there's 60% blue and there's 30% red and there's 10% yellow, then you've learned something about what you had to start. Of course, how you do that change, that flow, if you will, that flow of the painting, of that static painting into something that you understand what the end point is, or you hope you do, that's very tricky. I will say, again, though, one of the things that Perelman was able to do with Ricci flow that was very important, that was not as well understood earlier than his work, is dealing with the singularities forming. So you can start with your manifold, put your metric on it, have it change, but when it hits a singularity, the flow stops. So what do? You can either stop and say, well, I don't know what's going on, or you can do your surgery, figure out how to cut your manifold into two pieces, get rid of the part that has the singularity, and do it in such a way that it doesn't kill each piece, that it leaves certain aspects of each piece in a nice form, and then flow those and keep that going. Perelman figured out how to do that in a very nice way, and then based on that, a number of others were able to show that his ideas were sufficient for using Ricci flow to prove the Poincaré conjecture and the geometrization conjecture.
One last personal question. You said you haven't met him. I mean, you know most of the people in this field because it's a very exclusive field. Would you like to meet him?
Of course. And he was, for about a year after he put these papers out, I remember it was November of 2002, because I remember I was with a bunch of people who were really into Ricci flow in San Diego, and those papers came out, and we instantly just focused on trying to understand those papers. And they're very, very difficult. For the year after that, Perelman did sort of a world tour. I know some friends in Berlin. He came to visit them near Berlin. He came to MIT and gave some talks. And he did a bit of a tour. And if I wasn't busy teaching and just didn't have the time to really, well, maybe I should have done it. But anyhow, I didn't go to see him at any of these talks. Who knew that he was going to just immediately, or let's say after a year, go back into staying away from publicity? It would be fun to meet him. And people tell me, many of my friends in this field know him, and some of them have known him for years. In fact, he was apparently had a job in Berkeley maybe 20 years before. I don't remember. And then was it in the 70s or 80s? Probably in the 80s. So it was about 20 years before his big discoveries. And he wasn't as eccentric, but he was very focused. There are different ways of doing math. One way you can take some big problem like that and say, I'm going to just focus on that. The danger of that is you don't solve it, and then that's not so good. Or you can look at many different problems. I like to look at many different problems, not focusing on one particular one. But he would take that problem. In fact, from what I understand from friends who knew him, he announced at some point, I forget exactly when, many years before he actually came out with these papers, I'm going to use Ricci flow to try to solve the Poincaré conjecture. And he just, I don't know if he was doing any teaching at the time, but living in St. Petersburg, and then he did it. And actually, this is one of the nice things about the I'm thinking the nice things about this archive that instantly got his work spread to everybody. I guess in the old days, maybe these things would be sent out as preprints, which of course I remember those old days well, but I don't know if he would have had the resources to spread. It would have taken a lot longer for people to realize that this stuff was out there.
Do you remember it though? Is it like, where were you when JFK was shot? Do you remember your mate saying, "You've got to look at this thing on the archive, this is amazing"?
I do. I was in San Diego, and one of the people who knows a huge amount about Ricci flow is Ben Chow. And there was a small group there all the people working in Ricci flow at that time, they were very small groups. But there were about 3 or 4 of us, and I remember within a couple days, some people look at the archives constantly. I don't, I'm a little more focused than that. Well, I shouldn't put any, anyway, wasn't looking at the archive, but I remember when Ben Chow said, "This is amazing stuff. We're going to now have a seminar," and we met several hours a week, and we're going to study this. And each chapter, it was about a 7 or 8 chapter paper. We were each assigned a chapter, but it turned out that to understand a chapter took huge amounts of work. So he would put the ideas in there, and he would say, "And one can do this." And it would take months to show that you could actually do these things. And he had a couple of chapters which were kind of amusing in that he indulged his physics predilections and said, there was one chapter, in fact, it was, since I was the more physics-oriented of these people at San Diego, I was assigned this chapter, and it talks about entropy and some sort of fuzzy ideas, which may someday turn out to be important, but this, at the time, it wasn't clear. And still isn't clear how important those chapters are.
But was it an email? Did someone burst into your office and say, "Jim"?
Essentially, yes. Essentially, I mean, it wasn't an email. I happened to be lucky at the time to be in a group that with some of the leading experts in Ricci flow, Ben Chow in particular. And I think within a day or 2 of him seeing that, he said, "This is what we got to focus on." Laney was there. There were a number of us there, and we just focused on it. So I remember when he first told me, "This is something we have to look at." And again, the idea among the people who are doing Ricci flow, the idea that you might possibly be able to use it to solve the Poincare conjecture, to resolve the Poincare conjecture, or the geometrization conjecture was not outlandish. On the other hand, we had seen how some very, very powerful mathematicians had been sort of stuck. There were some important steps, in fact, dealing with that surgery to handle the singularities. They were really stuck, and they didn't know. I mean, there were ideas they had, and people like Hamilton still believe they can find a proof going around some of the not using all the tools that Perelman brought in. But on the other hand, there were a lot of people who had spent a lot of their careers trying to prove Poincare using very different methods, and I think they were completely shocked that you could take one of these flows, one of these things which is changing the geometry and time in a certain specified way, and prove something that has to do with a static geometry, if you will. And I should point out that since then, well, now there's probably literally 300, 400, 500 people at least working on Ricci flow. I mean, the fervor has settled down a little bit, but it's turned out to be a very rich area, and some other important, interesting problems, not as long-standing as Poincare, but also some very interesting ones that had been unsettled have been solved using Ricci flow as a tool. And these other things like the mean curvature flow, or a related one called inverse mean curvature flow, has been very important in proving something called the Penrose inequality, the Penrose mass inequality in general relativity. So these flows, the use of them in many, many areas of math has been established. And I also like to think that, I mean, not like to think, I know from talking to other people that you can use these to help make cartoon movies like Pixar and other places do. People working there will use these flows to make the motions of the characters more natural, if you will.
Sounds like you backed a good horse when you got into Ricci flow.
Yeah, Ricci flow is, my early career was in general relativity. Ricci flow is very different, but I liked both general relativity and Ricci flow are very much involved with evolving differential geometric structures. One is what's called wave-like, and one is heat-like, but very, very different, but also have similar characteristics and a lot of fun to play with.